created by MindSticks Foundation Trust. Welcome, class. Today, in this explainer, we're going to master the fundamental concepts of how chemical substances interact and exactly how we record these changes. Chemistry is happening all around us, every single second, and understanding how to write out these equations is your very first step to unlocking its secrets.
Quickly looking at our agenda for today's explainer, we will start with the basic changes happening in our surroundings. Figure out how to actually identify a chemical reaction. Define what a chemical equation is. Learn the 6 strict rules for writing them. And finally, look at the classic silver nitrate experiment. Section 1, Changes in Our Surroundings, Everyday Phenomena. Let's get right into it.
But before we jump ahead, let's do a quick recap. Can you recall what we learned in our previous standards about the valency of elements? We know compounds are formed by the chemical combination of elements, right? And the absolute main driving force behind forming these chemical bonds is just to attain an electronic configuration with a complete octet. Atoms will give, take, or share electrons to get there. Keep this basic principle in mind as we move forward.
Think about the everyday phenomena happening right in front of your eyes. The transformation of ice into water? Well, that is just a physical change. It's completely reversible, and the actual chemical composition of the water doesn't change at all. But consider the cooking of your food or a fruit ripening on the tree. Those are chemical changes. During these processes, the actual composition of the matter alters permanently, and whenever that happens, we confidently say a chemical reaction has taken place.
Moving on to Section 2, Identifying Reactions, Signs of Change. So how do we know for sure that a chemical reaction has actually happened? Imagine setting up an evaporating dish with some limestone powder and heating it strongly over the bright blue flame of a Bunsen burner. When the early scientists of the 18th and 19th centuries carried out fundamental experiments just like this, they carefully noted every single observation to see if the matter was permanently altering.
You see, the trick is knowing exactly what clues to look for. When we perform activities like heating that limestone or adding zinc dust to a blue copper sulfate solution, we have to keep our eyes peeled for physical hints. Does the reaction announce itself with a sudden change in color? Is there a visible release of gas bubbling out? Did the temperature shoot up? Or is there a fundamental change in the state of the matter itself? These are our vital, telltale signs that old bonds are breaking and new ones are forming.
Let's put some formal definitions to this, shall we? In any chemical reaction, the starting substances, the ones actually undergoing the bond breaking, are called your reactants. And the brand new substances that get created by forming new chemical bonds, those are your products. Think of burning coal in the air. The coal, which is carbon, along with the oxygen, are your reactants. And the carbon dioxide gas that gets formed, that is your product.
Section 3, Chemical Equations, Representing Reactions.
Notice the progression of how we record our science. Scientists don't really have the time to write out long, wordy equations. Instead, we use a much smarter, condensed format. By using the exact chemical formula of the reactants and products, we create what is known as a chemical equation. Just look at the bottom line. CuSO4 plus Zn gives ZnSO4 plus Cu. It represents the breaking and forming of ionic bonds in a highly efficient, globally understood shorthand. Section 4, Writing Rules, the 6 Conventions. Let's look at the rules of the game.
To make sure everyone in the scientific community is on the same page, there are 6 strict conventions we must follow. Rule number 1, we always write the reactants on the left-hand side and the products on the right-hand side. And we draw an arrow pointing straight towards the products to show the reaction's direction. Rule number 2, if you have 2 or more reactants or products, just seamlessly link them together with a simple plus sign. It's very much like simple maths, isn't it?
Next up is Rule 3, which is all about adding rich detail. We must indicate the physical states of our chemicals using lowercase letters in brackets. S for solid, L for liquid, and G for gaseous. Actually, if a gas is escaping, you can just use an upward-pointing arrow. If something is perfectly dissolved in water, we call it an aqueous solution and write AQ. And very importantly, if an insoluble solid forms, a precipitate, we clearly mark that with a downward-pointing arrow. This brilliantly brings us to Rule 4, which deals directly with heat. If heat must be supplied from the outside to force the reaction to happen, like when we vigorously heated our limestone earlier, we draw a tiny triangle symbol right above the directional arrow. On the flip side, if the reaction itself gets hot and releases heat into the surroundings, we literally write plus heat on the product side of the equation.
Finally, our last two rules. Rule 5 dictates that any specific conditions necessary for the reaction, say a precise temperature of 60 degrees Celsius, specific atmospheric pressure, or maybe the presence of a catalyst like nickel, must be written clearly above or below the arrow. And Rule 6 tells us that special information, like whether an acid is concentrated or dilute, gets written directly below its respective formula. Follow these 6 rules and your equations will be absolutely packed with detail.
Section 5, the silver nitrate experiment, a practical example.
All right, class, let's put all this theory into practice. Observe this experimental setup closely. Picture a conical flask filled with a clear sodium chloride solution. Inside it, carefully suspended by a thread, is a smaller test tube containing a silver nitrate solution. We seal the flask tight with a rubber cork, pop it on a balance, and record the exact weight. Then, we tilt the flask, mixing the two solutions together, and we weigh it again. Does the total mass change? No, it absolutely does not, but a very distinct chemical reaction certainly takes place.
The moment we mix them, an immediate chemical change happens. Following all our strict rules, we write the equation like this. AgNO3, plus NaCl, gives AgCl with a downward arrow plus NaNO3, See how we applied the rules? Both starting reactants are aqueous solutions. But crucially, look at the products. We place a downward arrow right next to silver chloride. That immediately tells anyone reading it that an insoluble white precipitate formed and settled at the bottom of the flask. It is a perfect textbook application of Rule 3.
Now here is a really fun bit of trivia straight from your textbook, just to help you remember this compound. Did you know that this exact same chemical, silver nitrate, AgNO3, plays a massive role in our everyday civic lives? It is actually the primary active chemical used to make that indelible voter's ink they proudly paint onto our fingers during elections. How fascinating is that? You see, chemistry isn't just confined inside a laboratory. It is out there in the real world running our society. So I am leaving you with a little homework task today. I want you to go and find out what are some other fascinating everyday uses for silver nitrate. Do some digging, keep these equation writing rules fresh in your head, and we will absolutely discuss what you found in our next class. Thank you for joining today's explainer, and happy studying.